The special cases of quadratic inequalities are easiest to understand graphically. I'm going to darken this x-axis here to make it really clear where this parabola sits. So we have x squared plus 1. This is the graph of y equals x squared plus 1 that we have drawn. And we are comparing it to 0, so we are comparing it to the x-axis. Just thinking about this by methods of solving graphically, remember that we interpret a greater than symbol as the word above. And so this is asking us for what values of x is that parabola above the x-axis. Well, note that the entire parabola, right, the entire graph sits above the x-axis. So that means for all values of x, this inequality is satisfied. And we would want to express this solution set then to be the set of all real numbers, which we can most easily abbreviate by this bold r. Or we could write that as the interval from negative infinity to infinity. The second one we would interpret as below. Since the graph sits entirely above the x-axis, it never sits below. So here we would say no solution. It turns out in this case, the second one of these is much, much less tricky than the first. Because what tends to happen if we are not given a graph is that we start by trying to find the real solutions. And we set this equal to 0. Well, very quickly we realize that this equation has no real solution. We get imaginary solutions. X is equal to plus or minus I. So because the equation has no real solution, often people jump to the conclusion that the inequality has no real solution. But let's remember the context of solving the equation. I have a number line. I want to mark the zeros on that number line. All this tells me, really, is that I have no real zeros to mark on the number line. Rather than that automatically meaning there's no solution to the inequality, it means that either the graph sits entirely above or entirely below, it never crosses. So what we would need to do, solving this symbolically, is again look at my inequality, look at the expression, and say this is a parabola that opens up. The only way this parabola could open up without crossing the x-axis is if it sits entirely above. And then this number line could be used to get both of these solutions. For greater than 0, we want the positive intervals, which is the whole number line. For less than 0, we want the negative intervals, which turns out to be no solution. So this isn't very tricky if we're solving from a graph, but it can be pretty tricky if we were trying to solve symbolically. A similar situation exists where we have a graph that just touches the x-axis in one point. So here's the x-axis. We'll darken it to make it stand out a little bit more. And our graph, we can see, just touches the x-axis, but otherwise stays on one side of the x-axis. Stays entirely above or entirely below. For this first example, we're solving the parabola, which opens down in this case, is greater than 0. I'm going to think of that as above. So I want the part of the parabola that is above the x-axis. I first note that none of it is above. I then have to stop and think about whether any of these endpoints would be included in my solution set. I want above, and this is a strict inequality. So I'm going to say this has no solution. Looking now at the second one, this is saying above again because it's a greater than or equal to, but it's an inclusive inequality. So the above part again gets us nothing But the or equal to in this greater than or equal to tells me that I should include just that one point where the function is equal to 0. So this would give me just the singleton value, we call it, 1. So it is possible for a quadratic inequality to have a solution set that's just a single value. It doesn't have to be an interval every single time. But it's only in these kind of special cases that that can happen. Going on to these other two, we then have below, but this one is strict, which means that in this case I do not want to include the intersection point, so I'll make that an open circle and make sure it's really clear that that's not filled in. I don't want to include the intersection point, but for below I do want the rest of it. I want this part and I want this part, and therefore my solution set here would be a union of two disjoint intervals from negative infinity to positive 1, union from positive 1 to infinity. This is how we use interval notation to just pluck out a single value, right? This is the whole number line except for the value 1. These have to be open brackets, otherwise this would be kind of pointless. Writing it as two separate intervals would be pointless if they were closed brackets, because it would really be the whole number line in that case. Because of the open brackets here, this plucks out the single value 1. And finally we have the inclusive form of this inequality, which would include the value 1, and in this case we would just write it as a whole interval, right? From negative infinity to infinity. We do not break it apart if our intent is to write the entire number line as our solution set. Or we could write this again as the set of all real numbers, bold R. So similar to the other case, this one is pretty reasonable to figure out if we're looking at a graph. But if we are solving this symbolically, we need to be comfortable having only 1 0 in our number line, right? We would solve the equation and get just 1 0 because this turns out to be a perfect square trinomial, so both factors are the same. Then I would still just want to think about the fact that the parabola opens down and say, well, the only way for this to open down and just touch at this one point is if it's below the x-axis on both sides of that 0. And then we could still use this number line to answer all of these inequalities by the same method.